Hey, what's up, guys? Chung here again. Today, today I want to talk about another LeetCode problem here. 1521. Find a value of mysterious function closest to target. So this is the last problem in the last week's weekly contest. It's a hard problem, and I wanna I wanna try to explain the concept for this problem to you guys here. So let's take a look. Basically, you're given like a function here. Let's uh, let's ignore the content of this function for now, and assuming you have this function here, and you are given like array here and the target, and you need to find out how can you get so based from this array and this function, what's the closest number you can get comparing to the target here. Basically, you're given this function, and you can pass in this array plus another two left and the right parameters, and then you have to somehow find the the minimum distance from the possible result you can get out of the function with this target value, right? And yeah, basically that's the problem here, right? And let's take a look at what does this function do. Basically, this function, what it does is you're given like an array here, and you pass a start and an end point. So for the start and end point, what it does is it does a bitwise AND for all the numbers from a start and end. Basically, you have an array here, right? You have many numbers on this array. Basically, you can pick any range. You can pick any range left or right, and this function will gives you the will gives you the will gives you all the bitwise AND for everything inside this range, right? And then it asks you to find the minimum values. Sorry, find a way to get the proper the proper proper ranged end result, bitwise end result for this range that has the closest target distance to the target. So how can we approach the solution here, right? So with the n here and the an array here, what does this n can tell us? Basically, one thing you guys need to know first is by the more numbers you are doing the AND, the less value it will become. For example, if there's a 3, whatever, 3, right? Not 3. Let's say there's like a number of 9, 80, 500, 400, 300, okay? And so on and so forth, right? It doesn't really matter. It could be could be 150. It doesn't have to be sorted. But the thing is, for the so this like this bitwise AND starts with 980, right? Basically, the more next time it's when it's do a bit AND with with this 850, the end result will definitely smaller than 980. Why? Because the bit end means uh, means it will only have this one value if both of the bit value is one, right? So this 1 1 will give us 1. anything with 0, 1 will give us 0, right? So it doesn't really matter because for 980, the biggest value for an end, bit end with this 980 is itself, because that's how we can get the most ones, right? Because we have to have the same. Let's say there's another 1 1. If the 1 0 0 0, how about it? This is 8, right? This, by the way, this is 8. And let's say there's another huge number here, right? It has so many ones here. But it doesn't really matter. It doesn't really matter how big the next number is, right? Because only these ones, only the ones will give us the end result ones. For all the others, as long as this number, as long as there's a zero number of value on the other positions, we'll always get 0, no matter how big the second number is. That's why every time when we have like a bit end with the current values, the maximum one is itself. So that's the sum will always like be smaller, equal or smaller than the current value. The more we are doing the end, the smaller it will become. So that's the fact we need to keep in mind. And with that fact, we can simply start our searching, and we can end our searching when it reaches certain conditions, right? So our goal is to try to search all the possible ranges, right? Basically, what we are doing is we're gonna start this L from every possible positions in this range, right? And then we're gonna try to do an end from the left all the way to the end, right? But we don't have to do an end for all the elements, right? Let's say, for example, we uh, we start this our search at this position, right? And then we just keep doing this end. By the time our current value, by the time the current answer is smaller, uh, less or smaller than the target, not the target, than the yeah, than the target, right? Then we can simply break, right? Why? Because we know the more will do end with the current answer, the smaller the value it will become. So by the time it already gets smaller than the target. So if we keep searching it, the answer will become smaller and smaller, and the distance from between the answer and the target will become bigger and bigger. So that's why there's no need to keep searching it, right? And that's when we stop, right? So that's the first stop, right? This is easy to understand. And the second stop is, do we need to search all the do we need to search all the L's here from start to the end, right? That's the second question. And the way to stop uh, trying the new position for the L is let's assuming from the current L to N. After doing all the bitwise N, we get a result uh, S here, right? Let's say if the current result from L to N, if the S is bigger than target, it's greater than target. If that is still greater than target, then it means we don't need to keep moving the L to the right side. Why? Remember, so the the more we do the bit end, the smaller the value we get. So what's the opposite statement for that? The less the less and we do, the bigger number it will get, right? So that's why on the stop to stop the L loop here, the outer loop here, because uh, we already do a bitwise end from L to N for everything, right? And the target is still greater than the 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 result is still greater than the target. Then it means let's move this L, assuming let's move this L a little bit to L plus one, right? Then it means the bit end will basically it means we'll do less bit end, which means the S can only be greater than the target. The S will be the S one will be greater than S, right? Because we're doing the last bit end, which means this S1 will be further away, will have like longer distance between this target. And if we move this L1 to L plus 2 here, right? And then from this L plus 2 to N, we'll have another S2 here. And this S2 will be even greater than S1 and of course greater than S and also greater than the target. Basically, the more we're keep moving the L to the right, the bigger S will get, and the further away it will become comparing to the target, right? So that's when we can stop the outer loop by checking if the final answer of the current loop is greater than target. Then we know, okay, we have already seen the best options yet already. No need to keep searching. Okay, I think that's pretty much the basic idea here. And let's try to code these things up, okay? And so the first thing is, of course, we need an n here. That's array. And the answer is the system maximum, since we're going to get the minimum value, right? So we initialize it with the maximum value. And then we have a L for range n. That's our left, right? That's our left. And the right, how about the right? The right is the same, right? The right is we start from L and we end with n. And then we have the bit result. So for bit result, we're gonna start with the array L, and for each of the right positions, right, we just do a bit result. We do an AND with the current right, right? We do this until, because every time, right, when we do another AND, we're getting a smaller number, and that's why we will be updating this answer, right, every time when we have a new result here. Gonna be bit answer dot absolute value between the bit result and the target, right? And we stop when the answer is smaller. So when the bit result is smaller, or equal to the target, break. You can do it smaller because if the answer is 0, right, then we simply return 0. At this moment, the bit result will be equal to the target, right? That's our ideal solution here. That's early stop. And like I said, and if this bit result is smaller than target, then there's no need to keep doing this bitwise AND because this bitwise will only uh, will only get smaller and smaller, right? And so that's the inner loop. How about the outer loop, right? So let's say if the bit result is greater than the target, right? Like I said, we can simply do a break here, right? Because in the inner loop, we will do a will break, right? Will break, and when this bit result is smaller than the target. And if it didn't break, or by looping through everything to the end, right? Basically, if this bit result target is greater than bit re, bit result is greater than the target here, it means that we must have already loop through to the last element, right? Because if it stops somewhere in between, it must be the only reason it can stop right in between is the bit result is smaller than the target, right? So basically, if it reaches here, it means that it didn't stop right in between. It means that we already looped through everything to the end, right? And if from the current L to the last element, if the result is greater than target, then we know there's no need to continue because, like what we discussed, the next bit result by moving the L to the right will only become even bigger, right? And which means it won't give us a better solution, better answer here. And then so in the end here we simply return the answer since we already keep updating the answers along the way. So yeah, I think this should just work. Let's in range. Okay. Okay, so this test case passed. Let's try to submit it. Yeah, so it didn't time out. At least it passed. Yeah, cool. So basically, and the time complexity for this problem, I believe the worst case is is n squared, right? Because we have a nested for loop here, and for if it's a worst case, our it will time out. But it didn't. It's because we have this kind of two breaks here to give us to help us stop the loop earlier. That's why it didn't end up with the worst case scenario, right? And yeah, just for the recap, so the key idea here is that the more we do a bitwise AND, the less value this bit result will become. With that in mind, first we'll stop the for loop when the current range is smaller, it's becoming smaller than the target, then there's no need to continue the inner loop. And for the outer loop, right, since the bit result from the starting point to the end is already greater than the target, there's no need to try another starting point because with a with a greater L starting point, the speed result will only be greater than the previous one. Okay, cool guys. I think that's it for this problem. Yeah, thank you so much for watching the videos and stay tuned. I'll be seeing you guys soon. Bye bye.